Our next speaker is Ovidiu Hutuleac, Senior Solution Architect at AWS. Ovi is passionate about helping developers and enterprises build modern applications using transformation capabilities of AWS services. His professional experience started in 2007, consists in different roles, ranging from software developer, database and sysadmin and DevOps engineer. He leveraged his experience to help people bring new ideas to life, focusing on data-driven architecture, distributed system, and DevOps culture. In his free time, he do triathlon. That's really interesting. Maybe I will meet Ovi on some Ironman races. Reads about human mind and emerging technologies. Today, Ovi share his experience in architecting for data-intensive workload. Hello, Ovi. How are you today?
Hi, Dimitro. Hi, everyone. Yeah, awesome. Actually, really awesome. Even if we have 7 o'clock here in Germany, and it's almost 8 o'clock with you, still happy and still excited to join the conference today with you guys.
Thank
Thanks for
you.
introducing.
So, yeah, stage is yours. Yeah, please go ahead.
Thanks a lot. Yeah, and thanks for having me actually today. Yeah, great. So maybe let me introduce myself first. I'm Ovidiu Hutuleac. I'm a solution architect here with AWS, based out of Germany, in Munich, so in south of Germany. I'm already with AWS like 2.5 years already, working mostly with enterprise customers, but really focusing on the data part, right? So everything about managing data, data in terms of databases, in storage, in terms of moving around data, moving and doing analytics maybe afterwards. So I'm gonna go over some patterns that we actually solve with the customers that we worked with, and I wanted to share with you as well how you build actually your application, how you think about your application in terms of data. So when the application is actually increasing in activity, usually this implies more data incoming, more data to be done. So this is why we call data intensive workloads and how we can deal with that. We're going to look actually first at the roles of the databases, that what the role do databases have now in the modern application, because it changed actually if you compare it to like 30 years ago. And then we're going to look at some dimensions to consider where you when you're designing your application from a data perspective, from data modeling perspective. And then we are going to look at some solutions that are out there for data storage and for databases, and what trade-offs are there to be considered when you choose your purpose-built databases or data store. And then we're going to take a use case, a specific use case, and just go step by step over it, just to show again what are the principles behind. Great. So if we think about data and data workloads 30, 40 years maybe ago, we only had like mainframe. It was one big computer, everything was sitting inside, compute, memory, storage, data, everything was there. So there was not like so many trade-offs to consider, right? It's how you scale your data, how you model your data, everything was in one place, right? And this architecture didn't really scale smoothly. So we considered to bring out the client part. So we had the client server architecture at some point, where the client was actually like a big fat client, and on the other end of the cable was a big database where you just interacted and modified and saved the data. And with the emerging of the internet in the 90s, we moved like to free tier application, right? So on one side we had the browser, so accessing over the internet, and on the other side we had this backend application and the databases behind the scenes. And this brought us some flexibility, of course, in terms of scaling, in terms of manageability of the application. And then we welcome the area of microservices, right? So microservices already known, and you saw already today the talk about serverless also microservices. It's awesome that we brought this architecture pattern into the application side, but we kind of left the database behind, right? So everything what was storage, what was designed to do databases, was kind of left behind at the beginning, and now it's catching up, right? So databases are catching also up, and there are more and more data storage built out there, which is purpose built, right? So for each requirements that an application has, you can use a different type of data storage or database, which meets those requirements. And why did we do that in the past was more about the modern application, which is emerging, right? So everybody wants to write modern applications today because there are different requirements out there. If you compare with 30 years ago, where we didn't have yet, maybe the internet was just emerging, now there are really, really other requirements. We are talking about millions of users. We are talking terabytes, maybe petabytes of data to be moved around. The complexity is increasing. The request rate is expected to be millions per second. You don't want to sit with your phone and wait for seconds for the response. It needs to be millisecond response, and it needs to scale. It needs to be cost effective, and everything over API. And yeah, I mean, how can developers today build such applications, and still meet all the requirements for the performance, scale, and availability? It's a big puzzle out there, and the first thing that you do, you of course you separate those applications, the compute part from the storage part, and this is the general pattern. But another pattern really emerged as well in the let's say in the enterprise actually. Which is taken everywhere. It was introduced by Robert C. Martin, is the clean architecture pattern behind the scenes, where you have in the center the policies, which you call it maybe the enterprise entities and the use cases of the entities, and around them you build more and more mechanisms to implement those rules, right? So think about a booking site, right? You have entities where it's a booking, maybe you have hotels, maybe you have guests. These are so entities there, and the use cases will be something like book me a room for a specific date, right? So how do you implement those use cases? Well, you do have some mechanisms which are in green here, something like you have maybe a presenter, a UI, which is presented to the user. Maybe you have some gateways to the databases who save that booking and maybe search for the booking for a specific date. And this way, the dependency rule actually is towards inner circle and not the other way around. So you to translate that in simple language, it's not recommended to have entities which have SQL code inside, right? So you always work on with the gateways, you always work with controllers and presenters in order to talk also with the web or also with the database. And this is actually what is the new role of database is actually modern application. We talk about databases as a way to implement a business mechanism, right? So the model that you built in your application, your core application, should be, at least at the beginning, really, really independent of technology. And once you choose your technology of the databases or the storage, you implement that over the gateway to kind of abstract that from the enterprise entities inside. And how are developers doing that? At the beginning, we are looking at our enterprise entities and our use cases. We gather some requirements, and then we define our entity relation diagram. And it's kind of funny because a lot of people, when they hear about entity relation diagram, the classical ERDs, they all think, it will be relational databases behind the scenes. It's not really true, right? This is a way maybe to model your data in the application. You didn't choose yet your database. You didn't choose your data store type. So you model your data, you write down your data access pattern, for instance, do a booking, search for booking, like in a booking website, and then you model your primary key, how you want to get that data, how you want to sort that data from the application side, what type of patterns you have, access pattern you have, and then you have maybe some secondary patterns, and you want experiment and you optimize, right? At the beginning, maybe developers just have like a JSON file with some mock data. That's their databases. They're implemented over the gateway, and it's total independent of technology. And then once you experiment more and you see some requirements of scaling, for instance, or requirements of computing, then you go to a specific data storage or to a specific database technology and you choose from that and you develop on that. And once you come to this point where you say, in my application, I need to choose a data store which has this, and this requirements. So I need to evaluate what options are out there. So how can I implement my requirements, my application requirements based on the on the on the data store that are out there. And there are a couple of dimensions to consider, right? So when we look at our application requirements and our data, we look at a couple of dimensions, right? So we look at the shape of the data. So how is the data? How is the data? How it presents itself, right? Is it presents more in rows? So you usually do updates on a specific row, so a specific column, or you're doing maybe some big documents uploading, or you're maybe unstructured, so you're moving PDFs around. So what is the shape of the data that you're trying to work with? That will be a very important dimension to consider when you work and you towards a data model and working towards choosing a data store for your application. The second one would be the size, and this is more about how big is one of my transactions, for instance. So how big is my working size? Am I working with rows like a transaction, or am I working with sets of rows like the last month, right? So this will be the size, the working size of my application. How can I do that? And how many transactions maybe per second do I need? So how many reads per second maybe I need? So that you look at the size as well before you choose your data store. And the third one, it's more about compute, right? So from the application side, you need data from the storage side, right? So it can be a database, can be just a plain storage there, like a NFS stay in there. You consider how much compute do I need to do on that data before I fetch it to the application, right? So maybe if I have a NFS, I just copy the whole JSON file and then I go over the JSON, I do some sums, I filter some things out. So everything is done in the application side. On the compute side, you don't really do a lot on the storage part, right? But at some point when you need more and more compute, like aggregations or things like that, maybe you take a database on that storage, and it has this capability for you, so you don't need to do that in your application. You just get the whole aggregation results directly in your application. So these are the three dimensions to consider when you choose your data store. If we go a little deeper, so if we look at the shape of the data, so I said a couple of examples will be like row store or it's column store. So you usually work on columns. Are you looking maybe at just putting and getting data? That will be like a tracking mechanism, right? You have some sensors, you're just putting, getting data, or GPS position. That will be great, like for a key value database. Or maybe you have some patient data. This is like documents. Maybe you want to index that document on specific attributes. That will be more like a document database. And then you have graph. So if you have relationship between your data, then of course you can use like something like for recommendations. That will be a graph database. Time series is just coming one after the other with the timestamp. So you want to do some aggregation as well there. White column blockchain. So even unstructured is also one shape of data, right? So if you think about binary files or videos or maybe just PDFs, it's also one type of data that you need to consider when you choose your data store. And the second one is I talk about already sizing and scaling. So you think about the size of your data. So how big is the working size, right? So am I working with a couple of active users? Am I working with the data from today or from the data from the last 12 months? So what is my working size? That will be an important question to ask. And another one is the size at limit. So think about, let's say, countries or cities. I mean, we're not going to have 1 million cities next day, right? Or next week. It's not going to just unbound scale. But if you think about sensors and maybe do some temperature or do some other metrics, you can be that you maybe tomorrow have a million more metrics incoming, right? So it's unbounded. So think about the size at the limit of your data, and this will help you a lot in choosing the right data store. The same with the caching, for instance, and the same also with partitioning. Is there a natural partition? Like a sensor data is really natural to have partition on sensor. But you think about company payroll, it doesn't really have a natural partition. You can partition on the person, but it will be really distributed. It will have a lot of partitions, not really grouped. Maybe you can partition on department, but it will not you will always have like departments which are really hot, so maybe big and have a lot of transaction, and others which don't have. So it's not really a natural good distributed partition if you think about company payroll. Great. Flexibility, like I said, you have the capability to do compute on top of the data before going back to the application, right? So you get already the aggregation, already the whole computation at the storage, the database layer before going to the application. That's an important point also to consider. Throughput latency, how often is your data changing? Like, I don't know, GPS data doesn't really get updated, so a new street coming, but inventory counts is just very, 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 very fast updated. Great. And then, yeah, so what the developers are doing, they're thinking about, okay, should I take a relational database or should I take a NoSQL database? That's the first question that you put in your head, right? And in many cases, a relational database will work just fine. It's awesome. I mean, if you think about again about the booking website, just have your hotel, you have a room, some guests, you make a booking and you send an invoice. This works perfectly, and I think even 2/3 of the application I saw, they are still running on relational databases, even if it's commercial or it's open source, it's just work very fine. So even if it's an old technology, it has many good use cases out there. You don't need to throw them apart. But many people just want to go to NoSQL. And if you think about NoSQL, it's just like we kind of trade off this flexibility of having multiple entities and just bind them around and join them however you want, with the winning of having everything denormalized in one document and getting that document only with one request. But you kind of give away a little the flexibility that you have from the relational database. And if you think about NoSQL, this looks kind of I don't know if you worked with commercial database, relational databases in the past, it's like a materialized view, right? So you take all the tables there, you join them together, you pre-compute everything that you want, sums and counts and everything, and you just put that materialized view in a document and just, hey, this is your NoSQL. So you kind of denormalized everything. You lost a little from the flexibility of doing queries on demand, but you won maybe more on the latency. And there are a couple of differences. So SQL is really good for structured rows. It's good for columns format. Query flexibility. I mean, relational databases are there to have ad hoc exploration without end, right? You can take every column from every table, join them together, do some sums, do aggregations. Really awesome. And this is shining actually in OLAP use cases. So where you don't really know exactly your data access pattern. So your business might come with a new access pattern. It's very nice to have like a SQL. You have this flexibility, but it's hard to scale, right? So having the data really bound together, right, with the others, like with the relations, it's hard to scale independent those tables, yeah, right? And This is why it's hard to shard and hard to partition that data, and this is hard to scale. On the other side, NoSQL was invented exactly for that, to tackle the problems of the SQL databases, which are hard to scale and partition and shard, by denormalizing everything. So when you denormalize everything and you shard everything on the primary key, then of course you can have multiple partitions which don't really have a lot of relation between them. And this is the promise of the NoSQL. You can have sharding data. You can have really fast and low latency CRUD operations, so create, read, update, delete. But you don't really have that complex computation of the SQL database, right? So you cannot do really fast count, sum, aggregation maybe about two tables. It's not really easy to do that in NoSQL, and you may need many requests to do that in NoSQL world. So it's really important to know your access pattern before you go to a NoSQL database, designed properly. There's some pitfalls as well. One of them is, of course, you saw that one is for scale, really hard, and the other one is defined for scale, should be easy, right? But there are still some pitfalls with scalability between SQL and NoSQL. On one side, scaling is in SQL is mostly vertical, right? You just put more things on top, or maybe you do some read replicas. But adding more indexes, or this will add more latency to your data, right? And it happened many times. I mean, I was DBA also in the past for a couple of years, and developers were coming to me and say, "Hey, Ovi, what did you change in the database? Because my application is really slow today." Look at them. Hey, me as a DBA, I didn't change anything because we do deployment every 2 or 4 weeks. So I didn't change anything. Okay, so I checked, I didn't change anything. And I asked the developer, maybe you changed something. So they looked at the application. No, nothing changed. But the application was still slow. So what is going on? So we just dig a little deeper. And actually, nobody from us did anything. The data just grow, right? So when the data grows, everything becomes slow, right? So data growth it will increase the query latency because you need to join maybe more tables or more data in the tables. Your sort and temporary file will be bigger. Your result set will be bigger. So everything is increasing because of the data growth. And of course, the log contention maybe will increase as well for the data and the amount of transactions. And that's one of the pitfalls. You cannot scale infinitely with your SQL. And that's the promise of the NoSQL. But if you don't know your data access pattern, then you may end up as also one of my colleagues who said, yeah, I will take NoSQL because NoSQL is good for everything. So she just took one table, put all the entities inside, and after 3 months, he had like 45 indexes on the NoSQL table. That was crazy because he didn't know the access pattern. He just added indexes for every access pattern. But for each index that you add to a NoSQL table, it needs to be updated every time someone does an insert. So every time when you do an insert, you actually do another insert in another 45 indexes to be updated. And this brings a lot of costs. It's still scaling, but it's really, really costly to have all the indexes there. And there are some pitfalls as well. With NoSQL, it's not a silver bullet. That's the idea behind. So the most important thing to understand between SQL and NoSQL is that there are technologies which don't really replace each other. They can coexist without any problem. But from your side, you need to understand if scaling actually is a problem you need to solve. And there are applications which just need to scale to maybe a couple of thousand of requests per second, and it works just fine with a relational database. So you need to know, is scaling a problem that I need to solve now? And how would they discover that? I mean, usually you look at 4 limits that you may encounter in a system. You look at your transaction per second. So if I add more and more CPUs, do my transaction per second in a benchmark remains linear? This is the ideal way, the green one. Or at some point, I get a transaction per second stop, actually, even if I add more and more CPUs. And that will be one of the inflection points when you say, hey, my system only scales until maybe here with the design that I have. and it's okay. I accept that because I don't need maybe more than 300 transactions per second. The other one is the queries per partition or per table. If you have hot tables, which are really, really asked, at which level are actually this data will be really slow or be throttled, and that will be one of the limits or your constraints of your system. The same with the lock contention. So it doesn't matter how many CPUs do I add. Once I have more and more and more sessions, it's just stacking at around 300 transaction per second, and because everything is locked. And the last one is about query latency. So when you query your data, at which level of number of sessions, so for instance, I have here around 350, 400, it just the query latency just explodes. It doesn't matter how much CPU do I add. And these are a couple of limits that you need to know from your application and accept them like constraints, right? You say in the requirements of the application, I don't need to have more than 1,000 transactions per second. So I design my system for that. And I know everybody wants to have unlimited transactions per second, but it will come at an additional cost, and it will come at an additional maintenance and at more complex design for application. So know your limits, accept the limits, and based on those limits, you can design your application actually really fast and maybe evolve from there. And I wanted to present you again something to maybe to think about when you choose your data store or databases, and based on free the Pi theorem, so free capabilities. And the Pi theorem was presented in a reInvent, I think 3 years ago. It states that between pattern flexibility, infinite scale, and efficiency or low latency, you can only have two at the same time. Yeah, so there's no system that can have free all of them free at the same time. And if you think about data models, so if maybe you have relational, maybe you have columnar or key value, document, or graph. So based on this, you can have a look at this Pi theorem and then choose maybe your data store. So for instance, on one side, we have this pattern flexibility and infinite scale. So this means I'm very flexible on what I want to query from my data and do computation on it. And it can scale up to terabytes, petabytes, but I don't really need efficiency. So maybe it takes a while, right? So these are the Pi parts. It'd be something like Redshift, if you know, and it's like a data warehouse. It just take a while until your query comes. It scales infinitely and has a lot of flexibility, but I trade off my low latency, right? I accept the low latency. The same with Athena, right? So just reading from S3, and it scales almost infinitely. And the other part, we have this pattern flexibility and efficiency, right? It's a really classical relational database if you think about it. But there are also other databases which categorized actually here. So we have the Aurora and the Amazon RDS, so the relational databases, all of them. And the OpenSearch is also pattern flexibility and low. And DocumentDB or Neptune, like a graph database. So these databases kind of trade off the infinite scale. I know at some point, it doesn't matter how much CPU I add, it's not going to scale linearly anymore. And I accept that trade-off. And like I said, it's still used. So relational databases are still used like 2/3 of the applications today, nowadays. It's worth to have a look at them. And on the other part, we have the infinite scale and efficiency, like DynamoDB, for instance. But I'm kind of trade off the flexibility, right? So I cannot do this aggregation and computation and all this flexibility that I have with the relational database, for instance. I kind of trade off that, but I want to have infinite scale and efficiency. And this is where really DynamoDB shines, or MemoryDB, like Elasticache, so data directly in memory, really, really shines. Great. This is a map of the AWS purpose-built databases. We are having so many services out there. Not that we want to be cool. It's because a lot of customers just asked us to have those services to meet different requirements or different purposes. So you can choose from them. You can experiment from them, and it's all managed. So you don't need to manage the infrastructure between that beneath that. Great. So I talked about theory a lot. So let's maybe jump into a use case. So I talk about the hotel booking, right? So I have a website where I want to put rooms and hotels, and guests maybe come and search from that website. And how do I tackle such a problem? So if I take the problem from the beginning, a typical developer or software architect would just look at user stories first and say, okay, so I need to have some managers who can add hotels, they can add rooms, and for these rooms can have prices for different dates, right? So just the managers just add the owners just add the rooms there, and on the other part, there are guests who are coming and they want to search for rooms. They want to filter those rooms. And maybe the guests want to book that room and maybe receive some similar recommendations, right? These are maybe the user stories in the first couple of iterations. So I look at the user stories. So what I do next, I just define my entities, right? So I have my entities and the use cases around them, like in the clean architecture. And I say, okay, I have a hotel and rooms and pricing and some searching. And based on the searching, I can do some booking and some billing. And the guest had some preference and recommendation. So I said, okay, just split it into domains because I don't have a big monolith out there. We talk about monolith and microservices today. So I just split it in domains now to have independent deployability and scalability. And I said, okay, I will start with 3 domains. At one at one domain part, I go a little deeper, and I said, what are actually my data access patterns? How do I access data? And based on those data access patterns, I can choose afterwards my data store, my database behind the scenes, right? So what I do is create, read, update, delete on room, hotel, and key based on primary key. I want to have maybe some available rooms for a given hotel. I want to have some available prices for a room and date. I want to update prices, so they're really updated in case someone books, it will not be available anymore. So there are a couple of data access pattern if you think about it, and hotels. When you filter hotels, when you search for hotels, they have multiple attributes. So it will be mm, many attributes incoming maybe with the time. So I recognize here I need some flexibility. I need to remain flexible here with the attributes, what kind of attributes are coming, where I'm searching, what I'm putting, what I'm getting. So first thing that comes in my head, like a possible design, no problem. I just take relational database. They're really flexible. So if a new hotel has a new attribute like seaside or has like free rooms to book, then I can just modify my relational model and it works just fine, right? So I have this query flexibility. But at some point, if you look at it from the guest bar, so searching, I need to have that search booking um, here. I need to have it very, let's say, current. I want to have it up to date. So how do I do that? So when someone updates price and the guest is searching, so I need to do the join again. So every time I do a join, maybe I do some a view on top of that, a materialized view. So I refresh it every time, but still the join happens every time I'm searching something, right? And at this point, this entity here will become hot, right? So it will be really, really hot. It will be a lot of inserts and updates from the producer side, so from the owners, but these prices will be also really, really asked from the search side, and it becomes really hot. And it's a hot object. And when you have hot objects, then you have bottlenecks, right? So, and at this point, I realized, okay, yeah, I think the price side is really hot. So there are a lot of unnecessary joins which are happening, but only from the search part, right? So from the room and hotel, maybe there's not so many, but from the search part, the joins are a lot and happening very often and consuming a lot of data. So I go back to design, right? So I say, okay, let's do a second iteration of design. So at one side, I have pricing and rooms and hotels, which are really low latency, no complex queries. You just put a room, get a room, put a price for a date, increase the price for a date, maybe make it not available anymore for a date. It's just get, put, get, put. So not really complex queries. That will be on one side. On the other side, I have this search, which is kind of needs to be flexible, right? So I need many attributes, multiple dates, and multiple working size. If you think about the scalability there, and latency is important, but not really critical. So I'm moving more from the low latency. Maybe it will be like acceptable latency in the search. You know that when you go on a website, you want to book something for a flight, it's just loading like 5 seconds. It's okay. I mean, it's not that bad. So it's acceptable trade-off. And I'll say, okay, great. So I have different data access patterns here in the same domain. So what I do, I just split the domain, right? So I split the domain because I want to have domains which do one thing and do it well. And I say on one side, maybe I'll just take DynamoDB and I will put everything there and get and put prices and hotels because I don't need complex queries. And on the other side, I need this flexibility to search on multiple attributes and still be fast, and I will take maybe like an open search service there. And yeah, it looks something like this. I mean, if you do your modeling for pricing in DynamoDB, will be a denormalization of your hotel and maybe dates and rooms. So you only put and get prices for a specific date, or maybe you put a new room there. Every time the owner or someone books something, you make it unavailable. And in the end, it could look something like this, right? So on one part, I have my API gateway. So that will be maybe the entry point in your application, where you say, okay, great, let's book a hotel. Let's put a price for the hotel. So the pricing for the hotel or the rooms or the hotel availability will go everything in DynamoDB. That will be the pricing. And on the other side will be search, right? So this is the search microservice. Maybe I'll have some fleet of containers there who are just running the search, an open search. But I need to bring the data somehow from what is happening in the pricing to the search cluster, right? So this is where, for instance, the stream, the DynamoDB streams comes very handy, because for each change in DynamoDB, you have the ability with DynamoDB streams to take that changes and maybe trigger a lambda function, or maybe put even a queue in between. I mean, we saw today the integration patterns also from Diana. So you can put also a queue in between or directly a lambda, and you can take those changes and then push it to your OpenSearch cluster and incrementally update and bring your search cluster to the current prices for the rooms and hotels. This is how it can look like. Of course, it doesn't stop here. So you always need to measure and improve. We only did like 2 iterations now, but still you need to ask a couple of things. Things like, where are my limits? So how much I can scale on this architecture that I built now. So how many transactions per second I have with the latency under 50 milliseconds. So I can run a benchmark and I say, I see that maybe at around 1,000 transactions per second, my latency goes up. So I know my limit. So I know the system will be performed very well until I reach that limit. So maybe I go again in another iteration of design, and maybe I redesign my application again to meet the new requirements. The same with the price changes, or how big is my delay. So when will the replication delay will be more than 10 seconds? So how much price changes will actually cause my search cluster to remain behind, right? And that's another limit that you need to know from your design. Or at which rate of updates I begin to see contention. So people trying to book the same room or book the same hotel, and the search cluster just cannot keep up. And once you want to book, it just said it's not available anymore. And when you see that contention happening often, then you need to have a look and do another iteration at your design, your possible design. Great. So we saw the use case, and of course, from here there are a lot of possibilities to go out there and still learn more and more about purpose-built databases and purpose-built data stores on AWS. you have the two big opportunities. So you have the skill builder on one side, which is digital courses directly online. So you can take advantage of that. And on the other side, get your certification ready. If you think about solution architect or being a database specialist or analytics specialist, then it's really encourage you to go there and get your exam. Great. I talked a lot. I want to stop here and see if there are questions about what I talked so far, and yeah, go from there.
Thank you, Ovi. Yeah, that's great insights. For me, actually, pipe TRM is something new because in architecture world we usually using cup TRM,
Yeah.
but it's really similar, yeah, to pipe TRM. So yeah, thank you for sharing this. And I would like to ask a simple question about DB monitoring in general. So maybe some advices, not about latency or CPU RAM usage, but some advanced monitoring where I can understand bad queries or some bad query plans, etc. So, for example, like SolarWinds, they provide such tool set to monitor SQL Server and other DBs. So, do you plan or do you have some insights to how to actually monitor our production?
Yeah, of course. I think that's a daily job if you are a DBA or you're evolving to maybe to a data architect. And yeah, it depends on really on the engine, right? So there are engines out there that you have, I don't know, MySQL, Postgres, maybe it's open source, or maybe you have commercial engines, and each of them have their specific monitoring tools. So you can go inside and see exactly what is happening at database level. The same, for instance, for the or DocumentDB, which has MongoDB compatibility. So you see the queries what are running, you see
Mm-hmm.
collections, throughput, and things like that. So there's no silver bullet. I don't think there's a tool out there which is just push your database, for instance, and do your DB monitoring. I will go for purpose-built databases and purpose-built tools which do the job easily. And maybe take an example. I can take an example of, for instance, even MySQL. You have MySQL 2 implementations on AWS. You have the RDS for MySQL on one part, and you have the Aurora MySQL, right? So they are really different in terms of scalability there. It's the same MySQL. We're not going to change the binary behind the scenes or things like that. It's the same compatibility. It's just the other way how we do storage behind the scenes. So on
Mm-hmm.
RDS, you have the classical host monitoring. You can have the database monitoring, the throughput, and the Aurora. You see more things maybe on the storage part. So how much IOPS you can increase that dynamically, and both have performance insights. So if you look at RDS performance insights, it's a way of sampling the database every second. So looking at the active session and say something like, this second I have 20 active sessions, 80% of them waiting on CPU, 20% waiting on storage. And performance insights comes at no cost for the 7-day retention.
Mm-hmm.
But if I take another example, for instance, let's say take Oracle, so you have also RDS with for Oracle
Yes.
on AWS. You can use both. You can use Performance Insight, which doesn't cost you anything. So it looks at your queries and your users and what is consuming from the events. But you can also install your Oracle management agent if you want on the instance, and then copy everything what the agent is scanning on the RDS, sending to the OMS cluster or the central monitoring, which maybe run on EC2, and then you can
Mm-hmm.
monitor with the specific Oracle tools. So you can do that as well. Yeah.
Mm-hmm. It would be great to have some CloudWatch integration with
You have
RDS and
CloudWatch
R.
integration.
Oh
You
yeah,
have
cool.
CloudWatch integration, but not with the Oracle tool, for instance, right? So you
Mm-hmm.
have CloudWatch integration with all the host monitoring, so enhanced monitoring, and also for database monitoring, but not for the
Mm-hmm.
exactly which SQL is running. Yeah.
yeah, we need some
Okay,
application performance monitoring for it. Yeah, thank you. Thank you. We
great.
have a few more questions. So, could you please advise which failover disaster recovery practice you are using for different kind of DB design?
Yeah, there are many out there, but there's one principle that we use also at AWS, and I say to everybody, um, we work from the use case or from the customer backwards. So first thing first, you need to define for your application what are your RPO and RTO metrics. So what's your time to recover and how much you afford to lose. And based on
Hmm.
those, you can have different patterns. The most common one is the pilot light. You just copy your data to another region, for instance, but it's not
Hmm.
brought up. It's just copied. You say it in S3, for instance, like copy a snapshot regularly. The next one is like the cold standby. So you copy the data and you still have a database which is running, but nobody's connecting there. It's just cold. And of course, you have the warm standby, which you still connect and you have it in another region. That will be maybe three fast patterns, but you always uh, take those use cases and see, do I really need to have a warm standby, which is costing me double, just to have the RPO of 1 minute, or is it okay 1 hour? Yeah,
That's right. Yeah, that's a great tactics. By the way, the all of them described in software architecture principle and practices book. Okay,
yep,
whatever.
I know it. Yeah,
I
yeah.
share. Yeah, yeah. So from Software Engineering Institute. Yeah, thank you for this answer. For the next one question, for read intensive and write intensive workloads for users around the world, what is your recommendation to come up with stable design? I
Read
think the
intensive
similar.
and write intensive.
Yeah.
Yeah, there are some requirements already, right? So we have the requirements there. What is write intensive? What is read intensive? I will ask first. Second, do you plan to have a global database or you have local databases all over the place? So what you can distribute and what you have in common. That is more like an application part decision. So do you really
Hmm.
want to have your customers in USA copy to Australia, or you only copy your maybe products or something like that? So it's more application design first. And then
Hmm.
once you model your data, um, you put your data in different regions and you define like a replication mechanism. And then at the replication mechanism, you have a look a couple of tools that are already out of the box. So you can do that, for instance, with Aurora. If you want to use a relational database, if you want to go to NoSQL, you have a look maybe at global tables from the DynamoDB. Or if you just say I have local databases everywhere, you can still have like I did now with the booking, right? You still have like a central search cluster which
Hmm.
replicates all over the place and does search locally. So yeah, define first at the application side which data you really need globally. And based on that, you define your access patterns, how you replicate that data um, to reduce actually cost and still meet the performance.
Hmm. But we also should remember about out traffic, right? Because traffic which is out from region, right? So it costs a lot, right?
It will
And
cost.
we need to care, yeah, about it.
It's a good point, and it works pretty well with the application design. Do you really need to move the data all around? So customers from SUA to Australia. So define first your domains there and see if you really need to copy everything.
Hmm. Thank you. Ovi, thank you for your great presentation. This is a question. What books can you recommend on this topic besides Design Data Intensive Application by Martin Klepman, if
Clipman, yeah,
yeah,
that's a good
correctly.
one.
So
Yeah.
yeah, any other?
So that's a really good one. The design data intensive. The talk is really inspired also from that. Another book that I really like is the from from Martin is the Clean Architecture. So Clean Code and Clean Architecture series is also very nice. And the pragmatic programmer, I like it a lot. I read it, I think, the second time this year. So look at pragmatic programmer. It's an old one, has many versions, but it's very insightful. And of course, the domain-driven design from Eric. Yeah, Eric Evans.
Yeah,
Definitely,
that's
it's
true.
classical ones. I know if you expected like a new book which is trending, no. If you want to learn about architecture in general, the architecture is an old problem. It's not a new one. So you read old books first, right? So the classical ones, and then you go to the new ones.
You are absolutely right. Yeah, all of these books written in 20, 25 years ago, and the problem still the same, right?
Yep.
Thank you for your time. Yeah, and for supporting our conference. It was a really great presentation, a lot of insights for me and for audience. Thank you for your time.
Yeah, thank you a lot for having me and for organizing this. So yeah, have fun, guys. There are still a couple of sessions to go, so hang in there. I'll be here.
Thank you.